Yesterday at the end we had talked about Schrödinger and how he developed wave equations, treating the electrons like waves, and that those equations allowed us to determine the probable location of electrons. And these are sort of like Bohr's energy levels. Okay, they're not quite as distinct. But his equations allowed us to make correct predictions for all atoms. There was still some debate about the nature of the atom at this time, and a guy by the name of Heisenberg came to realize that the atom is inherently unknowable. And that is something that is very alien kind of to our way of thinking. But he developed what we call the uncertainty principle. And it says that it is not possible to know the speed and the location of electron at the same time. And this is due partly to the fact that atoms are so tiny and electrons even smaller that anything that we use to try to probe the electrons or the atoms with drastically changes that atom or those electrons. We don't have something small enough that can probe these tiny particles without greatly affecting them. And so Heisenberg understood that, and this drastically changed our idea of how we understand the atom. We no longer try to think about what the atom looks like if we could see it under a microscope. We think about it more mathematically and understand that there is some inherent parts of the atom that are just unknowable. And there were a lot of people that really did not like this idea. Einstein was one of them. Schrödinger was one of them. But it has proven to be the best way for us to try to understand atoms. So the model that resulted from this work is called the electron cloud model or the quantum model. And let me explain it before you draw it, okay? Because even though it looks like a picture sort of like the others, it's representing something else. So let's imagine that we have, over here we have a tree with a beehive in it. Okay, I am not a very good artist, so you'll have to bear with me. And over here we have some flowers, a whole field of flowers. And then we have a big, big highway. Like, 8 lanes and no grass in there. And then, well, that's supposed to be the divider between the north and the south lanes. And then on the other side, maybe we have some different flowers. Okay. Now, if I have a camera set up and I take a picture every second for a month, I'm going to be able to capture places where a bee may be located. Okay, so let's imagine there's just one bee for right now because that'll make it a little bit easier. And so after a month, I take these pictures of where my bee is every second and I lay them on top of each other. Okay. And it comes out and it looks something like this. Because most of the time, the bee is close to its hive. And so there are lots and lots and lots of pictures of the bee in the region right around the hive. Sometimes the bee goes out to these flowers to find, some pollen. And so we do see that the bee is around this area. We never really see the bee in this region here. There's nothing for it to stop for. And over here, once in a while, it will travel this far to get some different pollen. And so after that month, we get what we call a density plot. And what this density plot tells us is where we are most likely going to find the bee. So if I am a bee hunter and I look at this density plot and I need to find this bee, where am I going to go first to look for it? To the hive. If I can't find it there, then I'm going to go to this field of flowers. Right? That seems to be where it is like second amount of time. I'm probably not going to go out into this busy highway to look for the bee, right? The chances of finding it here are very, very small. Well, this is what we do with the atom at this point. So what this picture is representing are the regions where we are most likely to find an electron. So we still have our nucleus in the middle, positively charged nucleus. But now this is representing a density plot of the regions where we are most likely going to find electrons. And we see that this region here is where we are most likely going to find an electron. And then there is a region where we are not going to find an electron, and there are no dots in there. And then a little bit further away, we have another region where the probability of finding the electron is greater, but not as great as this first distance. And then again, we have a region where we are not very likely to find the electron. And then another region where the probability increases. And so our model of the atom is now not what we think it would look like if we could see it under a microscope. It is based on where are we most likely going to find an electron. It's all based on probabilities and these mathematical equations. We can sort of think about these regions like Bohr's electron energy levels. Okay? They kind of correspond. The region where we are most likely to find an electron in hydrogen does correspond with Bohr's first energy level. Okay? But it is representing something just a little bit different. So this picture, you cannot draw solid lines. You have to draw little dots for it because it is a density plot. So hydrogen has just one electron, and if we were to somehow be able to set up a camera and take a picture every second for a month, where are we going to see the electron? We wind up with this kind of a distribution. Okay, so a description. The likelihood of finding an electron is based on probability. And in my picture, the dark regions have a greater probability of having an electron than lighter regions. Okay, so that's the description of the picture that I drew. Then we have three characteristics of this model that we need to understand. It is a mental model. It is not how we think it would look under a microscope. So whereas the previous models, especially the first three, the solid sphere model, the plum pudding model, and the solar system model, those are models that really reflect what we think it would look like. When we get to the Bohr model, it's a little bit more about how it works rather than what it would look like. And this really is not representing how it would look. It's a mental model. The electrons are thought of as waves. Even though we don't represent them as waves, mathematically they are treated as waves. And it's a mathematical model based on probabilities. We're not trying to say, this is where the electron is. We are saying, this is where it probably, this is where it most likely is going to be found. So it's a complete change from how we originally were trying to understand atoms. So on the test, these are two separate individual questions. You will be asked to give an explanation of the electron cloud model of the atom. So the explanation, that is this, right? You're explaining the model. Then separately you will be asked, what are three characteristics of the electron cloud model? And that would be this part here. Okay? And that's day 2. So those are two questions that you know are going to be on the test. So the last part then are problems with this model. We still don't have the final model of the atom. There are still things we don't totally understand. We think we have a pretty good handle on electrons now. Most of our concentration is on nuclear forces and particles that are in the nucleus. And so there are other theories out there that may lead to the development of the next model. String theory, for example, could be a theory that currently exists that may lead to the next model, although it's looking a little less likely for that particular theory. But we do not have any illusions that we totally understand everything about the atom. And so the work goes on. So maybe by the time you have children taking chemistry in high school, there will be some developments that have happened, and they'll have yet another model, a more complete model to have to learn. So I just want to review a little bit, give you a little bit more direction on exactly what you need to know from this chart and how you need to know that. So up here at the top, you have already been tested over the experiments and results for Democritus, Dalton, Brown, Thomson, Millikan, and Rutherford. You will not be asked questions about those again on this test. Now don't mark that out though, because when it comes semester exam time and you pull this paper out, you're going to want to be able to read that information. I told you yesterday there was going to be a chart that you would have to fill out for the models. I now have the test completed, made up, and so I can give you a little bit more direction on that. So how this is for the models, you will have to give me the name of the model, draw the picture, and tell me the problems with the models on that chart. The explanations are going to be separate individual questions. You must do them in chronological order, and you have to know what that order is for yourself. Okay? So you need to know that the solid sphere model came first, and then the plum pudding model, then the solar system, then the Bohr model, and then the electron cloud model, or the quantum model. Okay? So that takes care of the right half of this paper. For the experiments and the results, for Planck down to Heisenberg, you know that you are going to have to explain the photoelectric effect experiment. for De Broglie, Schrodinger, and Heisenberg, you basically need to know what is in these boxes right here. So for Schrodinger, all you need to know is he developed wave equations. And what they did was gave probable locations of electrons. Heisenberg developed the uncertainty principle. And it says that you cannot know the speed and location of an electron at the same time. De Broglie suggested that electrons may have a dual wave particle nature. Make sure that you understand that for him it's the electrons. And then for the experiment, you just need to know that they did an experiment with crystals and it showed that they did have, electrons did have a wave nature to them. So those are more individual questions about those people. For Bohr, there are lots of questions concerning spectroscopy and this hydrogen experiment, and we will talk about those in a little bit. This is more like what you did in your flame test lab, and you'll be getting those back here in just a moment, and we'll talk about that. For Einstein, you do need to know that he suggested that light may have a dual wave particle nature to it. Okay, that's the difference between Einstein and De Broglie. Einstein said maybe light has that based on those two experiments. And then De Broglie said, maybe there are some other things that have a dual wave particle nature. You will not have to explain hot object emission. It's listed in that chart that's on day 1, right? What are the experiments that show light is a particle? And we list hot object emission, photoelectric effect, and the hydrogen spectrum. But you will have to explain the photoelectric effect. Okay?